Hello everyone. Today we're going to take a look at root mean square speed and how it differs from average speed. So we're going to start with a little discussion of what we know about kinetic energy and temperature from kinetic theory. So according to the laws of kinetic theory, or the postulates of kinetic theory, we show that there's a relationship between average kinetic energy and temperature. Specifically, the average kinetic energy of the molecules in a sample of gas, which would be equal to the average of 1/2 mv squared for the molecules in that sample of gas. This average kinetic energy is equal to 3/2 times the Boltzmann constant times the Kelvin temperature of that gas. So this is a relationship that can be derived from the principles of kinetic theory. What we want to take a look at here today is if we take this relationship and we attempt to solve for velocity. So if I look at the second and the third terms here in this equation, and I say, okay, I know the temperature of my gas. I want to solve for the V in this 1/2 mv squared term in this equivalence. What is the significance of that velocity? So first, let's go ahead and solve for V in this case. If we were to solve for V using the second and the third terms, we find that V is equal to the square root of 3 times the Boltzmann constant times the Kelvin temperature divided by the mass of the gas. So this is an important result in kinetic theory. It's an important result for us as we talk about heat and temperature and molecular speed distributions in physics. We need to understand, though, what the significance of this calculated velocity is in the scope of our discussion. This is not average velocity. When you calculate this value V, taking the square root of 3 times the Boltzmann constant times the Kelvin temperature divided by mass, you are not calculating average velocity. What you are calculating here is what is referred to as root mean square velocity, or root mean square speed. We're going to use the term speed here for our discussion today. So root mean square speed is sometimes just referred to as RMS speed. So you might look at this and say, well, hang on a second. Didn't we use the average kinetic energy to find this value for V? Yes, we did. Well, then shouldn't that be the average velocity of a particle of gas in this sample of gas? And the answer to that question is no, it wouldn't be the average velocity. What you have to remember is that the average kinetic energy is based on the square of speed or velocity, not directly proportional to speed or velocity, but equal to or proportional to, we should say, the square of that speed or velocity. So this is a little bit more complicated concept than just saying this is average speed. Instead, this is what's referred to as root mean square speed. So just to illustrate this concept, let's take a look at a sample set of data and compare and contrast average speed with root mean square speed. So let's say we have a set of, I don't know, let's go with 4 speed values, 5.0 meters per second, 10.0 meters per second, 15 and 20 for our last 2 values here. So we've got 4 particles in our sample of gas. We measured somehow, let's just pretend we measured the speed of these particles, and we ended up with these 4 values. So if I want to calculate the average velocity of this set of velocities, it's very simple, right? V average is going to be just the sum of the individual speeds, and then we're going to divide by the number of speeds in the set. I know I'm dropping sig figs here, but this is just in the interest of time, so don't read too much into that. So I'm going to add up and divide by 4, and I'm going to get an average velocity of 12.5 meters per second. Okay? Everybody knows how to calculate an average. That's easy enough. So what we're going to do is record this value and kind of put it off to the side for just a second. So let's put it down here in the corner. V average for my set of data, 12.5 meters per second. We'll come back to that value in just a little bit. What we're going to do next is calculate the average of the squares of those velocities. So instead of just taking the average of the velocities, because kinetic energy is proportional to velocity squared, I'm going to take the average of the squares of the velocity. So what I would do to calculate that root mean square speed or velocity would be to take each speed, so I got 5 squared plus 10 squared plus 15 squared and so on. And again, I know I'm dropping sig figs here. I also didn't put my units in the calculation, but this is all just in the interest of saving a little bit of time with this video. So I'm going to go ahead and add those all up, divide by the number of elements, and then I'm going to take the square root. So what I'm doing here is I'm getting the square root of the average of the squares of the velocity. And that would be the root mean square velocity. So what we end up finding here is that our root mean square velocity or root mean square speed comes out to be 13.7 meters per second. So take a look at that. Average velocity we calculated earlier to be 12.5 meters per second. Root mean square velocity for this set of velocities is 13.7 meters per second. So they are not the same thing. When we calculate V from the K average equals 3/2 Boltzmann constant times Kelvin temperature equation, we are not calculating the average speed or velocity of a gas particle. We are calculating the root mean square speed of a gas particle in that sample of gas. So they are very different in terms of their mathematical computation. They are very different conceptually. We need to be sure we understand the difference between root mean square speed and average speed, or root mean square velocity and average velocity. So what's interesting then is if we take a look at a Boltzmann distribution. So let's get a Boltzmann distribution up here. On the Boltzmann distribution, if you look at the value associated with the peak of the distribution, so we're going to pick the most probable speed here, or what you guys would know from math class as, as being the mode of this sample of speeds. So this is the most probable speed. That is actually not the average or the root mean square speed. So this is something that can be a little bit confusing when looking at these Boltzmann distributions. The speed that is associated with that peak is simply just the most probable speed of that particular speed distribution. It's not the average, it's not the root mean square, it's the most probable speed. And this distribution is not perfectly symmetric, and that is hopefully going to help you understand conceptually how the most probable speed can be different from either the average speed or the root mean square speed. Realistically, we find the average speed is a little higher than that most probable speed, and that makes sense based on the shape of this speed distribution. So this is now what we're looking at, V average on my Boltzmann distribution. And the root mean square speed is a little bit higher than the average speed, as we saw with our sample calculation just a second ago. So our root mean square speed might show up right here on our Boltzmann distribution. So this would be V, did it again, fix that. Give me just a second, I'll get this figured out eventually. There we go. So again, this value then is our root mean square speed. So we see that is three different notable speeds on our Boltzmann distribution. We've got the most probable speed, which is associated with the peak in that Boltzmann curve. We've got the average speed or velocity, which is going to be a little bit higher than the most probable, and the root mean square speed or velocity, which is a little bit higher than the average. Okay, so that's a quick overview of root mean square speed, how we can look at it quantitatively, how we can look at it graphically, and how we can think about it conceptually.